Good afternoon, everyone. My name is Jakub Kozik, and I'm going to say a few words about a long-standing open problem and some small improvements that I managed to obtain in one of its specific variants. I suppose that most of you have met before a situation when we can use the probabilistic methods to quickly prove that objects with certain properties exist, but when it comes to constructing such an object deterministically, things get nasty. Probably the most famous example of this kind of mysterious structures are graphs with large chromatic number and large curve. In this talk, we will focus on a similar problem from the realm of hypergraph colorings. We start with recalling the basic definitions. Hypergraph consists of a set of vertices and a family of its subsets that are called edges. And a hypergraph is called K-graph or K-uniform hypergraph if every edge has exactly the same size and the size is exactly K. We are going to work with vertex colorings, and such a coloring is called proper if no edge is monochromatic. The one that you can see in the picture here is not proper because of this bottom edge. However, recoloring just one vertex is enough to make it proper. It turns out that just two colors are sufficient to make this problem hard and interesting. In this talk, we follow a sacred tradition and use colors red and blue. Erdős and Heinel in 1961 suggested studying the following extremal parameter. M of k is defined as the minimum number of edges in a k-graph that is not too colorable. You can see here the best bounds that we have for this function. Both were obtained by probabilistic arguments. So it frustrates me a lot that the upper bound by Erdős has not been proved for a long time, especially since the argument is quite straightforward. So he proved that uniformly random k-graph with this number of edges built over a set of vertices of this cardinality, k squared over 2, is not too colorable with high probability. So that clearly certifies that such hypergraphs exist. Let us take a quick look on the short story of the upper bounds for this problem. The first result, that was already mentioned in the early paper by Erdős and Heinel, contained the following simple deterministic construction. We can start with 2k-1 vertices and then build an edge out of every k subset of this set. Clearly, such a k-graph cannot be properly colored with two colors, but the number of edges being roughly 4 to the k is quite large. This little c in the formulation here, it indicates that we are talking about constructive bounds. In year 1964, Abbott and Moser came up with the first non-trivial deterministic bound. They showed a construction which, given two uniform hypergraphs that are not too colorable, combined them to build another hypergraph with larger edges that is not too colorable as well. That construction justifies this inequality, and then the inequality can be used to obtain this bound. Almost 50 years later, this constructive bound was improved significantly by Heidi Gebauer. She designed a very neat construction which allowed to reduce the base of the exponents to the right value. As you can see, the factor 2 to the k here is inevitable by the nature of the problem. I think it came as a surprise that a succinct construction like that can give an outcome that is so small. I spent some time playing with this construction and trying to understand its behavior better. And at some point I found a way to improve it. And that is the main result that I'm going to speak about. So we take a quick look on Gebauer construction, and we start with putting some auxiliary structure on the vertex set. It is convenient to organize the vertices of the constructed hypergraph into rectangular array. The number of columns is S, and the starting number of rows is 2t minus 1. So S and t are the parameters of the construction. And the constructed hypergraph will have this number of vertices. Every cell of the array represents a vertex. And at some point, every such vertex will be given a color, either red or blue. We are going to need a few more definitions. So, in a colored array, a color is dominating in a row if most of the vertices of the row obtain that color. We will also say that the row is mostly red or mostly blue. So here we have example of mostly red row. And ties can be resolved in an arbitrary way. We will also say that a sub-array built of some set of rows is consistently dominated if each of its rows has the same dominating color. So we advance to the construction of edges. And the edges are produced in 3 stages. Every stage corresponds to branching of the construction on some parameters. In the end, all the edges produced in the branches are gathered together to form the edge set. In the first stage, we branch on every choice of t rows. It means that the subsequent stages of the construction will be carried out on every set of t rows of the original array. The number of choices in this stage is written in red here. From now on, we can imagine that we work with a fixed choice of t rows. And in the second stage, every row is going to be shifted cyclically by some value. And we branch the construction again on every choice of such sequence of shifts. The number of choices is s to the power of t, written in green here. In the final step, we branch on the choices of k over t columns of the shifted sub-array. For every such choice, we collect all the vertices of these columns and make an edge out of this set. The number of choices in this step is written in blue here. Now, since the current number of rows is t, and we choose k over t columns, the resulting edge indeed has size k as demanded. That is the whole construction. It produces some k-graph, but in order to guarantee that the graph produced is not too colorable, we must pick large enough s. And at this point, the best value for s is this one, k over t times 2 to the power of t. For this value of s, the above formula can be simplified or rewritten to something like this. And remember that we still are free to choose t. And inspecting this formula, we can learn that t equal to cubic root of k is quite close to the optimal value. And then the total number of constructed edges becomes a number like this, 2 to the power of k plus something of the order of k to 2/3. Now we would like to improve the construction. And you can see that using every choice of rows and every choice of sequence and every choice of columns seems like an overkill. So it's natural to look for some smaller sets of candidates which would be good enough for the construction. It is rather easy to replace the set of all choices of rows with some smaller set. But that change can only improve lower order terms of our exponent. As you can see, it affects only this summand. So we are going to work instead of replacing the set of all sequence of shifts with something small. Before we start, we have to to understand what is really demanded from the consecutive stages of the construction. So the objective of the first stage is to guarantee that in every coloring of the array, for at least one choice of rows, the subsequent stages of the construction are carried out on a sub-array that is consistently dominated. In some sense, it mimics the naive approach of constructing non-two-colorable hypergraphs. Then, in stages 2 and 3, they have to satisfy the property that whenever they work on a sub-array with a consistently dominated coloring, they produce a monochromatic edge. So from now on, when discussing colorings of the sub-arrays in stages 2 or 3, we will always assume that it is consistently dominated. And we will also assume that red is the dominating color. The natural first step towards the improvement would be to determine the number of shift sequences that, under fixed, consistently dominated coloring, produce monochromatic edges. The sequence of shifts is called good if it produces at least k over t red colors. And the original analysis of the procedure uses the following argument. So fix a coloring in which every row is mostly red. And now, if the shifts are chosen at random, then we expect about s times 2 to the power of minus t red columns. And for large enough s, this value is greater than k over t. It means that for some choice of shifts, we indeed have at least that number of red columns, and hence the edge built from these columns is red in the considered coloring. That is clearly correct, but we can try to squeeze something more from this observation. For example, for the random coloring, close to half of the shift sequences are good. So in order to tackle pessimistic cases, we generalize the property of being good, and our first generalization addresses prefixes. So again, for a fixed coloring that is consistently dominating, the shift sequence of length I is good, or good so far, if the array of the first I rows, shifted accordingly to the sequence, has at least s times 2 to the minus a red columns. Now we can consider the following question. Suppose that we have a sequence of length I that is good so far, and we ask in how many ways we can extend it by one value in such a way that the extended sequence is good as well. It is tempting to answer that half of the choices are good, and that would be true for many colorings, but it's not true in general. So, more appropriate answer would be that large fraction of the choices are almost good. To make this statement precise, we relax our definitions and allow to lose at each step slightly more than half of red columns. Precisely, with each extension, we want to preserve at least 1 minus epsilon over 2 fraction of red columns. So we will work with epsilon equal to 1 over t, and since we still need, in the end, k over t red columns in the shifted array, we have to increase s, the number of columns. But it turns out that it is sufficient to multiply it by Euler constant. So from now on, we will work with this altered parameterization. And within these terms, we can give a precise meaning to the correct answer. So large fraction means about epsilon over 2, and almost good means just epsilon good. The extension property that we have just discussed allows to derive some bound on the number of epsilon good shift sequences. With that bound at hand, we can show that there actually exists a small set that can be used in the construction instead of the set of all shift sequences. And the easy way to prove it is by probabilistic argument. So indeed, it turns out that random set of shift sequences of size roughly this, 2 to the t log t, has the desired property with large probability. And recall that the desired property is that for every consistently dominated coloring of the array, at least one element of the set is epsilon good with respect to that coloring. So instead of the set of all shift sequences that were used previously, we use much smaller set S. And plugging it into our construction allows to reduce the number of outcome edges to the claimed value, like this. However, the work is not done, since we want our procedure to be deterministic. So it's high time to take a look on the randomization techniques. And we start with preparing some tools. So set R of sequences of numbers of length d is a combinatorial rectangle if it can be represented as a Cartesian product of d sets of numbers. And for a finite space, like m to the power of d, the volume of some of its subsets, like R, is just the fraction of the elements of the space that belongs to the subset. In 1997, Lineal, Lube, Sachs, and Zuckerman proved the following theorem. They were interested in sets that intersect every large enough combinatorial rectangle, and they derived an explicit construction of such a set of quite small size. In this formulation, capital D determines what size of a rectangle is large enough. The constructed set has number of elements that is expressed by this formula, and the construction itself is based on walks in expander graphs. In the case of our interests, for every consistently dominated coloring, the volume of the set of epsilon good sequences is at least that number. And if we want to hit every combinatorial rectangle of that volume, we can use the above construction to obtain a set of size roughly this, 2 to the something t log t. That number is not much larger than what we would get from the randomized construction. But unfortunately, the sets of epsilon good sequences do not form combinatorial rectangles. So our work is not finished yet. Okay, so let's start with altering the way that we represent the sequences of shifts. Recall that in the original construction, we first choose shifts for every row, and then we choose every set of k over t columns. And you can easily see that such construction is redundant, and in fact every edge is produced s times. To get rid of this redundancy, we can fix sigma 1 to 0, so that the first row is not shifted at all. The constructed hypergraph is the same. It also shows that our bound on the number of edges can be improved, but this improvement turns out to be insignificant. Now, instead of choosing absolute shifts, sigma 2, sigma 3, and so on, we prefer to work with relative ones. So R12 denotes how much the second row is shifted with respect to the first row. R23 denotes the relative shift of the third row with respect to the second row, and so on. As you will shortly see, it is convenient to organize these relative shifts into a complete binary tree structure. So we have a binary tree that is labeled by relative shifts. The nodes of the tree are in a natural way partitioned into levels. Level 1, level 2, level 3. And we are going to transpose the idea of epsilon good shift prefixes to our tree structure. If we take a node of level j, we say that it is epsilon good, or rather the labeling is epsilon good for this node, if first, all its descendants are epsilon good, in this case those two nodes, and second, if we take the array of rows corresponding to that node and all its descendants, in this case that would be these 4 rows, and we shift that subarray according to the relative shifts of the subtree, then it would contain a large number of red columns. And the meaning of large is expressed here. The exponent 2 to the power of j here is just the number of rows in the currently considered subarray. What is our transpose definition? And we are going to assign the relative shifts level by level, starting from the bottom, and trying to build an epsilon good leveling of the whole tree. The crucial observation here is that when we consider some level and assume that the lower levels are already labeled in an epsilon good way, then the epsilon good choices for distinct nodes of that level are completely independent. And you can easily see this because they depend on disjoint sets of rows of the array. But that means in particular that the sequences of epsilon good choices for the current level form a combinatorial rectangle. And since the lower levels are already epsilon good, the volume of the combinatorial rectangle is under control. So we can use the lemma of linear Lube, Sachs, and Zuckerman to construct small heating sets for every level, and then we combine these small heating sets into a heating set for the family of sets of epsilon good labelings of the whole tree. And that is the final set that we use in the construction, instead of the set of all shifts. It turns out to be small enough to justify the client result. Okay, so just to summarize, the original construction used every choice of rows, every choice of sequence, and every choice of columns. And we managed to replace the set of all shift sequences with carefully crafted set of much smaller size, and at the same time, the smaller sets still guarantee that the construction works. It means that the construction produces a hypergraph that is not too colorable. So the second factor of the original counting formula can be decreased to this value, and although we had to increase the number of columns a little bit, that change turns out to be insignificant. The new formula is minimized for t that is close to square root of key over log key. And for this parameterization, we obtain in the end the number of edges that is expressed here. 2 to the power of k plus square root of k times some polylog. So that is all. Thank you for your attention.